Assalamualaikum warahmatullahi wabarakatuh and very good afternoon to all students. Okay, today we will meet again for another chapter under computer architecture and organization. So last week we have been discussing about the computer system and the components inside the computer. So this week we will discuss about the number systems of the computer, okay, which is the language that has been used by the computer itself. So thank you for the support for all my videos. For those who subscribe to my channel, hopefully this will benefit you all in your studies. So for those who haven't subscribed my channel, please do subscribe, and I appreciate if you can drop a few likes on my videos. Okay, so let's start with our class for today. So this week chapter is about the number system. So basically, what is a number system? So number system is a system that we use to symbolize or to communicate of certain values in our life. Like for example, if you have numbers, for example, quantity of certain things, in order to communicate about those quantity efficiently, we use this number system. However, there is a lot of symbol involving number system, and depending on the civilization involved creating the number system, they are different in representation. So for example, in Egyptian number system, okay, you show here left, you can see at the beginning is almost countable, and when it's got more than 10, okay, you see that it become another symbol entirely. So this one is not a representative of a good number system that we can use these days. And another example is this one, which is by the civilization of Roti. So you can see that we have different kind of representation of numbers, okay, within the number system. So number system is useful when we want to use it to quantify things. However, when the things got too many, okay, when you want to do a calculation with it, a proper number system is required. Okay, you cannot do a calculation with a people subtract with a frog. So this kind of number system is difficult for us to do calculation with. So with our current number system that we have, which is the decimal number system, okay, so decimal number system is based on the Arabic letters. Okay, you see in Roman letters, you see the number system in Roman letters also difficult for us to calculate. So what we use right now is based on the Arabic number system, which is the decimal. So for computers, we have 4 types of number system that we use exactly. However, basically, the one that being processed by our computer will go up until we'll only use binary. However, on top of it, user in assembly language or even in our user defined function, we can go up until decimal based on the compiler itself. So basically, the 4 number system that we are using right now is base 10, which is decimal, base 2 which is binary, base 16 which is hexadecimal, and base 8 which is octal. So what does it mean by base? Okay, if you base on 10, means that there are 10 digits in the numbers, which is start from 0 until 9. So when it finish, okay, you will increment to the left and start with 1, and on the right will remain back to 0, which is 10. Okay, and then it will increment again until 99, and then when it goes into 99, okay, we'll increment 1 on the left, and the 9 will revert back to 0, and another 9 will revert back to 0. It becomes 100. Okay, so the same concept is being used for binary, hexadecimal, octal as well. So binary, instead of having 10 digits, we only have 2 digits, which is 0 and 1. So firstly, what happened, okay, when you have 0 and you have 1, when you want to go to 2, okay, the 1 will revert back to 0, and it will increment on the left, okay, as 1. Okay, so that's why we have 10 in binary is 2 in decimal. Okay, for hexadecimal we have 16 digits, which is from 0 until F. So what does it mean by 0 until F? So you have 0 until 9 and then continue with A, B, C, D, E, F. Okay, so that's why you can see that the representation of hexadecimal includes alphabet as well. Okay, so after after F it will revert back to 10, and then it goes to 11, 12 until 1F, and then it goes back to 20 and continue up until FF. Okay, and then go back to 100. So if you convert them into decimal, it will be entirely different numbers than in hexadecimal. So usually hexadecimal is used to represent large decimal number, okay, or large binary number, okay, in our computer. So and then the final one is octal. So octal is basically based on 8 digits, which is from 0 until 7. So after 7, it will go until, after 7, it will be 10. Okay, after 17, it will become 20. Okay, so this is how it works in the computer. So again, okay, so what we use every day is the decimal number system. Why we call it decimal? Because it is based on 10 and is multiplied by 10. So here in this case, 4,728, you got 4 times 10 power of 3 plus 7 times 10 power of 2 plus 2 times 10 power of 1 and 8 plus 8 times 10 power of 0. So the total here you got 4,728. So here, in case you have a bigger number, okay, so you have the preface using a certain symbol to describe the number, whether it's too large or too low. Like for example, you have tera to describe 10 billion. You have giga to describe 10 million. Okay, you have mega, I'm sorry, giga to describe 10 billion. Okay, so mega to describe 10 million. Okay, and kilo to describe 10,000. Okay, so here you have including up until -3 until -12. Okay, milli, micro, nano, pico. So this is based on the radix of 10. So when we look at binary, instead of 10, we are talking about 2. So if you say that it's a 100 in binary, means that 1 times 10 power of 2. Why? Because 10 power of 2 here? Because it is in the location number 2. So here is location 0, location 1, location 2. So 1 times 10 power of 2, 0 times 10 power of 1, and 0 times 10 power of 0. So total of this is 4. Okay, in this case here, the total of it is 43. Okay, it goes up until 2 power 5, which is at this location, which is the 6th location, is 2 power 5. So binary is basically very difficult to human, okay, because you need to read all the digits in order to understand, and there are a lot of digits. Okay, so we are usually more comfortable with numbers since we have 10 fingers. With decimal number system, we have 10 fingers, so it's easy for us to calculate using decimal. However, conversion between binary and decimal, okay, so they are complex. However, it's not that difficult for us to do. Okay, but in case we want to do it fast, okay, it's very, very time consuming and frustrating for you to conduct it properly. So in this case, if you see, okay, we have 110111. So here we have, okay, so here is 1 times 2 power of 0, 2 power of 1, 2 power of 2, 2 power of 3, 2 power of 4, 2 power of 5, okay. So here, total of this, you can get 55. So when we talk about the binary system, we also have representation using prefix, which is under giga, mega, kilo. Okay, so the power of 2, usually in representing kilo, you have 2 power of 10, which is the total value is 1024. 2 power of 20 means 1,048,576. This is mega. And 2 power of 30 is giga. So that's why when we buy a hard disk, like for example, you buy a hard disk of 1 GB. Okay, actually it doesn't mean that it has only 1 billion 1 billion byte. It has more than this because it is calculated based on the radix of 2. Okay, the binary is calculated based on the radix for 2. Okay, so then we have hexadecimal. So hexadecimal is basically for us to simplify the binary representation. So when you have 4 binaries, we group them and represent them by using hexadecimal. So you have 4 binaries here. If representing 0, it becomes 0. 1 become 1. Okay, 6 becomes 6, 7 becomes 7, and up until F. F is 1, 1, 1. All ones become F. Okay, all zeros is 0. So from the right, you increment 1. And then go back to 0, increment 1. Go back to 1. Okay, and the increment doesn't increment here, 1, 1. And then when you increment another one, 0, 0, 1. Okay, okay, and then 0, 1, 0, 1, 0, 1, 0, 1. Okay, so here we start from the right side. So here 1, okay, and then when you want to increase it, it becomes 10. And then next you increase it, it increased by 1. Okay, here, and then when you increase this 2, it becomes 100. So you will increase up until F. So this is the hexadecimal system. So basically, since it is represented by 16 hexadecimal digit, so this is what we call a base 16 number system. So means that if you want to convert them into decimal, you have to times with 16 power of something based on the location. So in case of here 2C, okay, you need to what you need to do is that you have 2 times 16 power of 1 and C times 16 power of 0. C in decimal is 12. So you have 12 times 16 power of 0 here. So the total of this is 44 in decimal. Okay, so it's easier to convert between binary and hexadecimal. Okay, so binary to hexadecimal and hexadecimal to binary is easy by using converting only 4 digit by 4 digits. So if you have 4 binary, you can convert it immediately using this formula. Okay, for example, you have 0, 0, 0, 1, 0, 0, 0, 0. So immediately you can know that it's a 0 and 8. Okay, or 0, 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay, so immediately you know that it's a 7F. Okay, so it's easier for you to convert using binary to hexadecimal. Okay, so basically, if we talk about decimal, okay, you have 0 until 15. This is where hexadecimal is represented from 0 until F. So you have 16 digits here. Okay, so the binary of this is basically an increment of 4 digits binary. Okay, up until from 0000 until 1111. Okay, in terms of a fraction representation, okay, so previously, before this, okay, I show you how we convert using fixed point representation. Means that we start with 2 power of 0. Okay, so for floating point representation, we doesn't start with the 2 power of 0. We start with which decimal point it started with. In this case, if you want to convert from decimal into binary, okay, binary, how do I convert them? Okay, in this case, like for example, we start with 2 power of negative 3 here, okay, and then 2 power negative 1, 2 power of 0, 2 power of 1, and up until 2 power of 4. Okay, so here in this case, okay, what we do is that, okay, we convert them. Okay, in this case we have this binary here. Supposedly there are point here. Okay, there's a point in the in this line. Okay, this line we have a point. So here in this case you have 2 power 4 in case of 16. Okay, we want to convert this value actually. Okay, so you have in 16 you have 1. Okay, and then 2 you got 1. Okay, 1 here, and then next is 2 power negative 0.5 and 0.125. So the total of here is 19.625. So the binary is 1001 10011 dot 0.101 here. Okay, so this is basically how you represent fraction. So let's take a look. Okay, in terms of fraction, usually we are represented based on the data types. Okay, so some data types, okay, in programming you have integer data types, float data types. So data types is used to represent the bits for representing those numbers. So in this case, okay, for floating point representation here, we have 32 bits where 8 bits will represent, okay, the exponent here. So means that 14, 15, 16 is represented under this, okay, in the front. And then the significant here is in the front, okay. So significant here is basically the one in the front here. So the mantissa here is the significant. Exponent here is the bias exponent. So if you say that 1.59 means that here is basically they will change it into 159. So 159, okay, and then the bias here is 14. Okay, bias is 14. So the sign, okay, sign here is the negative, whether it's positive or negative. So in this case, here we have it representing the sign whether it's negative or positive. So other than numbers, we use the ASCII code, okay, here to represent the binary as well. So in case you are typing characters based on your keyboard, okay, like for example, you have alphabet in your keyboard, so your keyboard will push out, okay, the binary that is being represented by this hexadecimal here. So in case of 20 means that is 00100000. Okay, so this is representing the alphabets. Okay, so you have this ASCII table. If you have a certain binary, you can convert those binary into alphabets, okay, based on this ASCII table. Okay, so you have other than ASCII, like for example Unicode. Okay, so all of them based on certain standards of design for us to communicate efficiently using the computer for based on the binary itself. So the binary also representing colors. Okay, so previously we have 256 colors. So how many bits that representing 256 colors? So 2 power of x. So x is basically 7. If you have 2 power of 7 bits, okay, means that you have 7 bits, okay, so you can have 256 options of colors, okay. So now these days we have 24-bit color, so means that you have 2 power of 24 options of colors available in your PC. So how many bits? Okay, it's a lot, more than 16 million possible colors with 24 bits. Okay, so next, okay, I would like to teach you how to convert from those number system. So firstly, okay, let's take a look at binary to decimal. How do you convert from binary to decimal? So basically, okay, the way you convert from binary to decimal is basically the numbers times 2 power of the number location. Okay, start from the right is location 0, location 1, location 2, location 3, location 4, location 5 here. So start from the right, okay, 0 until 5. So calculate 1 times 2 power of 5 plus 0 times 2 power of 4 plus 1 times 2 power of 3 plus 0 times 2 power of 2 up until 1 times 2 power of 0. So the total of this values, this equation is 41. So you got your decimal already here. Okay, so when you want to convert from decimal to binary, okay, we do a divider, remainder method, okay, here. So how do you do it? In case here we have 26 decimal, want to convert to base 2. Okay, so first we do 26 divided by 2 is 13. So there are no remainder, so it becomes 0. And then we pull down, okay, 13, and then 13 divided by 2 is 6 with remainder 1. So here the remainder 1 becomes the next number. And then 6 divided by 2, we got 3. Remainder 0. So in this case 0. And then 3 divided by 2 is 1 with remainder 1 here. And then 1 divided by 2 is 0 with remainder 1. So your binary that you get for 26 decimal is 11010, which is, this is the binary 11010. So in case of floating point number, okay, how do you calculate? You convert them into binary. So in this case, floating point number, when you want to do it, you need to start with 0 point something, 0 point something. So here, okay, for real number here in this case, okay, you start from the right, but the floating point number you start from the left. So here in this case 0.875 times 2, you got 1.75. So the 1 here will become the remainder. So 1 you pull out and put it in the front here, and then you push down the 0.75. So 0.75 times 2, you got 1.5. Okay, pull out the 1, the next one, and then you push down the 0.5. Okay, and then you times 2, you got 1. Okay, push out the 1 and pull down the 0. And at the end, you got 0, which is the end of the binary. So the binary in this case you got is 0.1110. Okay. So when you want to convert from hexadecimal to decimal, okay, basically you need to do the same thing like the binary, but however, since it's a base 16, okay, you need to use the power of 16. So in this case, you have A3F, 16, you want to convert to decimal. So A times 16 power of 2 plus 3 times 16 power of 1 plus F times 16 power of 0. So A is basically 10, F is basically 15, and you total them, you got 2,623. Okay, and when you want to convert from decimal to hexadecimal, okay, you just divide it by 16. Okay, so here the same thing, we use the remainder method. So 425 divided by 16 is equal to 26 with remainder 9. Okay, 26 with remainder 9. So 9 will be pulled out and put at the back. So and then the 26 will be pushed down and divided again with 16, which is equal 1, where the remainder is 10, which is equal to A. So and then you pull out the A for the next digit. And then the last one, 1, okay, you push down 1 divided by 16 equals 0, okay, which is you have the remainder 1, and you pull out 1 as the last digit in the hexadecimal. Okay. So finally, how to convert between hexadecimal and binary. So this one is easy. If you have a hexadecimal, okay, so you have 110 DE1, sorry. So D, okay, in hexadecimal you got 1101, E is 1110, and 1 is 0001. So you combine all of them, you got the binary. And when you want to reverse from binary to hexadecimal, here you just divided 4 digits and you convert the 4 digits into the hexadecimal separately. In this case, you got 9 and 1, and here you got 91 in hexadecimal. Okay. So next is we have octal. Okay, so octal, for you to conduct octal, basically you have to do binary first. So when you convert to binary. Okay, so hexadecimal in this case convert to binary. You got this number, and when you got this binary, you separate it to 3 digits each. Okay, hexadecimal using 4 binary digits, but octal you separate using 3. So in this case, when you separate using 3, you got 100 is 4 in binary, 001 is 1 in binary, 100 is 4 in binary, 111 is 7 in binary, and 001 is 1 in binary. So you got, okay, so you got here 17414 is an octal. Okay, so 17414 base 8 is the value of this octal number. So when you want to convert it back to binary, you just convert this into 3-digit binary and combine them again, and you got the full binary. And you can do, you want to convert using into hexadecimal or decimal, is up to you. Okay, so my advice, when you want to convert number system, basically the easiest way, okay, if you want to convert any number system to decimal, convert it to binary first and then convert the binary into decimal. So in this case, okay, you will make your calculation easier. Okay, when you want to convert decimal into certain number system, like for example octal or hexadecimal, convert them into binary first, and then from the binary separate those binary to become hexadecimal and octal. Okay, so okay, that's all for the first half of the number system chapter. Thank you very much for paying attention to what I'm teaching. So I hope I can see you again on my next video. So stay tuned. I will upload my second part of the video soon. So for those who subscribe and like my channel, thank you very much. For those who haven't, I would appreciate your subscription and your likes. So I see you guys next time. Thank you. Here, Dr. Sharif Fauzi Kamruzaman, presenting from University Malaysia Pahang. So stay safe, stay healthy, and take care. Bye-bye.